Welcome to Differential Equations, Section 3.2. In question 1 here, we want to use the Wronskian to determine if the set of functions that they are giving us are linearly independent on the particular interval in question. So, what do we have? We have f of x is 17, g of x is 6x, h of x is 2x squared. And the interval in question is the entire real line. So, to form the Wronskian, we've got our three functions across the top row, their first derivatives and their second derivatives. All right, so I have f of x is 17. First and second derivatives are 0. G of x, first derivative is 6. Derivative of that, 0. H of x is 2x squared. Derivative for x. And the second derivative is 4. So I've got this 3 by 3 determinant. And I'm going to be expanding by the first column. So if I expand by this first column, I'm going to use the 17, cover up this row that it's in, this column it's in, and the subdeterminant is the one that's in here. And so to get this one, this is easy. 6 times 4 is 24, minus the upward diagonal, which is 0. And I get 17 times 24. And so the Wronskian turns out to be 408. And that's clearly not 0 on all of the real number line. Now, just to recall for a moment, 3 by 3 determinants can be expanded by any row or column that you like. You just need to remember the sign of the position. And the sign of any position is minus 1 raised to the I, the row, plus j, the column. So you see here, position A12, the sum of the indices is 3 minus 1 to the 3 is a negative. So again, you can expand by any row or column that you like, and you typically pick one that is convenient. So as an example, I've got a 3 by 3 determinant here, and let's say I wanted to expand by row 2. All right, well, looking at row 2 here, let's scroll up just a little. So row 2, the positions are minus, plus, minus. And so the position here for the 1 is minus 1. You cover up the column and row that it's in, and you're left with 1, 3, 3, 2. The 2 position is a plus, so plus 2. Again, cover up the column and row it's in, and you get 2, 3, 4, 2. And the last one is a minus 1, but the position is a minus. So minus a minus 1, and then the subdeterminant, cover up the column and row, and I get 1, 2, 4, 3. Also, just to remember, with constant coefficient second order homogeneous equations that look like ay double prime plus by prime plus c, y equals 0. There should be a y here. Equals 0, we have the characteristic equation. And if I have two real roots that are distinct, then our general solution looks like that. If I have one real root that is repeated, then I have c1 e to the lambda 1x But since it's repeated, I've got a x e to the lambda 1x. And if I have two complex number roots of the form a plus or minus bi, then I get a e to the ax on both of these, right there and right there, cosine of the I part and sine b for the I part. So, looking here at question 2, we have a third order problem. We have three initial conditions, and so these are constant coefficient, homogeneous. So I form the characteristic equation. I get r cubed plus 9r is 0. I can factor out this common r, and so I get r equals 0. And then from this particular piece, I get two complex roots. So 3 plus or minus 3i, or of the full complex form, 0 plus or minus 3i. So the e to the 0 part would be missing. So I just have the cosine and sine pieces. Since r is 0, e to the 0 is 1, so I just get the constant. And so there's my basic solution for our third order problem. So if I differentiate this once, differentiate it twice by the chain rule, we get that. And so now, what were we given? We were given that y at 0 was 4. All right, well, let's see. Cosine of 0 is 1. Sine of 0 is 0, so I get this first relationship, c1 plus c2 is 4. Y prime at 0 is minus 1. All right, well, the sine would be gone, and I just get 3c3. So c3 is minus a third. And if I look at y double prime at 0, well, again, the sine term is gone. I get minus 9c2, and so c2 is a minus 2/9. And if I plug that back in to my first relationship, I get that c1 is 38/9. So my general solution for this third order constant coefficient homogeneous differential equation looks like that. In question 3, we have a non-homogeneous constant coefficient differential equation. So if you look here, we've got y double prime minus 2y prime minus 3y is equal to 6. So it's not 0. Two initial conditions. So if I first solved the homogeneous one, I get r minus 3, r plus 1. So we get two values for r distinct. And so I get c1 e to the minus x, c2 e to the minus 3x. Now they already gave us that. So this yc, the complementary solution, is the solution to the homogeneous one. And then they're giving me yp, being minus 2, as a particular solution. And you can see that it does work because you've got minus 3 times the y would give you the 6 on the right. So I'm looking at forming my general solution as a combination of those two. So I find y prime. I'm given y at 0 is 8. Okay, so that would be c1, c2, minus 2. Move the minus 2, and I get this first equation. If I use y prime at 0 is 14, I get my other equation in C1 and C2. And so I've got two equations and two unknowns. It's nice these add up directly, and I can get 4C2 is 24, and I get C2 is 6. Well, if C2 is 6, 6 plus 4 would be 10, and I get my general solution here. All right, in question 4, they are showing me a particular form for a second order non-constant coefficient homogeneous equation. And they're saying that if I know one solution, y1 of x, then I can use something called the reduction of order by letting y2 be another function times y1. This will give me my second linearly independent solution. So the question is, well, how do I do all that? Okay, so let's take a look. So in this case, we're going to be given this particular differential equation, and they're going to tell me that one answer that is guaranteed is x squared would solve this. All right, so what do I see about y2? y2, they told us by reduction of order, is v times y1. All right, so plug in y1. All right, so I need to figure out what y2 would look like. All right, so let's see. The first derivative by the product rule would look like this. And now if I differentiate this again, I've got two product rules. That's why you see 4 terms there by going through the product rule. So now come back to the equation and let's plug in what I know about y2 double prime. All right, I need y prime, so y2 prime is there. Plug that in. And then finally on the end here, I've got y2. y2 is just x squared v equals 0. So what I did then is just grind through all of that stuff. X squared distributing in, 4x distributing in. And so then I started looking at, well, what goes together? Well, let's see. I've got a v double prime. Don't see any more of those. All right, so that's that term. What about the v prime? All right, I've got a 4x cubed, another 4x cubed. That's there. Now the v's, let's see, got a 2 there, an 8 there, and a minus 10 there. And so those completely cancel. All right, so we are down to this equation involving the second derivative of v. All right, so let's clean this up. Let's bring this stuff to the right. All right, so now once I move the x cubed to the right, I'm going to get the x's on one side and the v prime items on the other. Okay, so that looks good, and this simplifies to minus 8 over x. And then this is okay. It is undefined at the origin, but if you remember up here, they told us that the x of concern is greater than 0. All right, so I'm going to integrate both sides. Well, if I integrate this, I get minus 8 ln absolute value of x plus c. And what about this thing? Well, let's see. If I integrate this, I get the ln of the denominator. Let's see if we believe that. If I differentiated this by the chain rule, I'd get 1 over v prime times the derivative of the inside part, which is just v double prime. All right, so I'd like to get my hands on v prime, so let me take e of both sides. All right, so if I take e of this ln, I get v prime back. Like we've done previously, I'm going to take this minus 8 here and shove it back up as an exponent. We're going to get a e to the c, so just call that c. And so now I get a relationship about v prime. All right, well, that's pretty easy. If I can integrate this, so v is going to be integral of x to the minus 8. So add 1, divide by the new exponent. All right, and so I get that v is 1 over x to the 7. I don't need any of the constants. All I need to figure out is v. And so y2 then is going to be that v times y1. And y1 was x squared. And so my y2 answer is 1 over x to the 5th. And that concludes the discussion for this section.